Welcome. Whether you design a game or a plot of a novel or a model for physics, you have to first of all set the stage. You have to build the arena space in physics, or build the board for a game. You have to have the actors, the pieces or matter in physics, and you have to have a time evolution, which is the plot in a play or the rules of the game. And then we have forces, which are how do these actors interact, relations or laws, and the forces in physics. This week I was implementing a cellular automaton which I call the standard model game. It's a game which you can play and then you can watch what happens. So you set up the stage, you take a simplicity complex, you put it in the actors, you put in the matter, and then you let it evolve. And I am guided by simplicity. I want the simplest possible setup. And for geometry, I take a finite abstract simplicity complex because it has just one axiom. It is a finite set of non-empty sets closed under the operation of taking non-empty subsets. You cannot leave that away because the geometry is not that interesting if you just have a set of sets. And what we have is also, we have to say something about maximal simplices. We want to have a geodesic flow. We want to have a Hopf-Rinow theorem. That's another assumption which, for example, the simplest way to say it's a Dehn-Somerville manifold, or manifold. You can also just assume it's a discrete manifold. That works. And in a discrete manifold you have just the property that a q-1 dimensional wall has exactly two maximal simplices attached. So two triangles here on a two-dimensional manifold. So this is an assumption which we have seen gives us a nice geodesic flow, and these are the rules of this geodesic flow. I like dihedral time because I want to have a infinite dihedral group as an action. So there are reasons for this, and here also practical reasons. You want to easily to be able to invert the map. And so if you write the map as a product of two involutions, then we can just switch A and B and we get the inverse. So it immediately shows that this is invertible, and we have also just a fast way to implement the inverse. But here are the rules. We have looked at that. A is actually just going from the simplex to the neighboring simplex, and it's an ordered simplex. So we have ordered simplices here, which the ordered simplices, ordered maximal simplices, form what I call a frame bundle, right? They define a coordinate system on, at each point, and the points are the maximal simplices. And so what we have then is we have this natural way to go from one simplex to a neighboring simplex. And if there should be none, we just leave that with the identity at the boundary. For example, here in this implementation here, I'm looking at the manifold with boundary, and at the boundary just reflects, and it has the effect of a billiard, produces a billiard flow. And then we have the second thing is a rotation of the orientation. We need something abelian. We don't want to have the order matters if several particles come together, and that R depends now on the structure of the particles which come in. If we want to have involution, we need particles and antiparticles. Of course, that's also motivated by physics, because in reality we see particles and antiparticles, and so we have two branches. These two branches, one is modeling the particles, one is modeling the antiparticles. And so they can cancel out, right? If x and y are the same, they essentially cancel out, and nothing would happen here in the game. But if you take another particle there, then they start to interact with this particle-antiparticle pairs, and it's not trivial here. So we have just started with one Meson or Baryon. I don't remember what I took at the beginning, and I just see what happens when I let it evolve, and it produces a lot of other particles. So the only law is that we want to have the law. It should be local, it should be at the point. So that's a cellular automata assumption, a locality assumption. There should be causality assumption. We should only have what happens is only depends on the simplex which we have. And the most natural thing is what we do is we just take all the particles, we add them together, positive particles positive, the negative particles negative. We make the prime factorization because the primes behave like hadrons or leptons. That's an old story. And then the most natural thing is to take the Liouville function because it's completely multiplicative and it's uniquely defined. If you, a completely multiplicative function is defined on the primes, and in these orders, both the complex plane and the quaternions are very natural. They are the only associative division algebras, real division algebras. That's why it is an interesting structure. And also the number theory is interesting because we have unique orders, maximal orders, which are the Hurwitz integer, Hurwitz-Lipschitz integers in the quaternions and the Gaussian integers in the complex plane. And then, so this is essentially unique. You don't have a choice there. You also have unique prime factorization, essentially modulo gauge transformations or switching of the units. Units are, of course, not commuting, so it's more interesting in the non-abelian case here. And so we will come to the units. They kind of are, behaving like Force Bosons. So that's what we have as on the particle side. And for the interaction, we just take a completely multiplicative function. I think maybe it's more natural even, to consider some primes are Mesons and some primes are Baryons, depending on whether there are 2 quarks or 3 quarks. This is all just number theory. Actually, not even number theory, it's just basic combinatorics of these orders. So what we have is, so kind of maybe more natural is just to take here R equal to -1. If it's a fermion, if the total number of particles which you get here, when you do the thing, you get a fermion, or when you have a boson, you take 1. Maybe that's the more natural thing than to treat all primes the same. It is a matter of fact that the primes in the quaternions are either kind of Meson-like or Baryon-like, or, and that's the two, it's kind of plays a special role. It's a ramified, case. It's kind of the only case which is kind of where there's no kind of, it's not a Meson, it's not a Baryon, so it is special, and it behaves a little bit like a force carrier, massive force carrier. If you look at the norm as the logarithm of the norm as a mass, you take the logarithm of the norm, then it's additive. Mass is an additive notion, and so we have kind of gauge bosons in the form of photons, or we have massive bosons, and we have gluons. So kind of if you bend the interpretation, like in chess, right? In chess we have interpretations of the soldiers are the pawns and the rooks are maybe the cannons, and kind of nice associations. That's the only thing which we currently have, nice associations with particle physics. I like to call it the standard model game. The game is motivated heavily by mathematics. So we have, first of all, we have a Hopf-Rinoff theorem, we have differential geometry, we can look at curvatures and all kinds of things. We could look at general relativity notions like sectional curvatures, Ricci curvatures, and scalar curvatures. We have here also prime factorization, which brings in a particle-like nature, and it's completely deterministic and completely determined if you make some assumptions, like the assumption that maybe fermions should be treated in one way, bosons should be treated in another way. But it's highly non-trivial. Because what happens is if you take these particles come together at some point, they can have different orientations. They kind of come together, and then together this prime factorization can become, you know, rather, so the electrons can become, you know, other particles. So we have all kind of transitions which are possible, and one of the, you know, big questions is what kind of transitions are possible, and you know, also if you look at more heavy particles which are made of other particles, like, you know, modeling a nucleus, or not modeling a neutron, or modeling a neutron which is kind of an electron and proton together, whether how fast do they actually travel. So we expect them to travel slower, because what happens is if you have particle-antiparticle pairs everywhere, the whole process here slows down. And can imagine that there are situations where kind of these particles move also on geodesics, but slower, because they are kind of going through all kind of different interactions locally with particle-antiparticle interactions. So it's a little bit like quantum field theory, where you have these very complicated things happening, and what you see is kind of you observe some scattering amplitudes, and that would be then kind of interesting to study here, what kind of scattering amplitudes are possible. But anyway, that's the proposal, and I put the code then up. You can experiment with that, and that's it for today.